Hello there, and welcome to your next lesson on further GCSE mathematics. So today we're moving on to an entirely new topic, probably completely new to most of you, which is calculus. And in this first lesson, we're learning about something known as limits, which is not specifically to do with calculus, but it features very prominently, and it's a technique that um, we need to be able to understand in order to understand calculus. And it's a technique that I imagine many of you have not encountered before. This concept of limits. So yeah, it's worth dedicating a lesson to this concept because it can be a tricky thing to wrap your head around. So first of all, we're going to look at asymptotes, which is like a little limit, which you may have encountered before when graphing particular functions, like say like y equals 1 over x, which is a type of rational expression, and asymptotes appear. If you haven't, don't worry, we'll be looking at these from scratch essentially. Look at what an asymptote is, when they appear, and how to work with them. And then we're going to look at the limits of rational expressions. So an asymptote is already a type of limiting behavior. Um, and we'll see how do we calculate a limit and what their uses are. So first of all, an asymptote. What is that? So asymptote is we refer to an asymptote in the context of a graph. So when we have a graph, and an asymptote is essentially uh, a line. Could be any line, but we'll only deal with it when they're straight lines. It's basically a line that a graph will gradually converge towards, but it will never quite touch. So converge means to get closer and closer and closer to, but it never quite reaches it. It just keeps getting closer and closer. Like imagine if I kept half in my distance away from something. So I move half the distance, then half again, then half again. You'd imagine you'd keep getting closer and closer and closer, but you'd never quite reach it. That's essentially the concept of what an asymptote is. And we get two different types that we will be dealing with. We have horizontal asymptotes, which are what occur horizontally on a graph. So, okay, as we're going out to the far along the x-axis to positive infinity and far in the other direction to negative infinity, how does y behave? Does it just keep going up and up or forever or keep going down? Or is there an asymptote? Does it converge towards a particular value? That's the idea of a horizontal asymptote. And then we have a vertical asymptote, which is the result of an undefined value for a function output for a given x input. So that's basically like an actual uh, value in which the function just doesn't work. So the best way to look at that would be with an example. So say if we have a graph here, and probably the simplest rational function you could come across is just this, y equals 1 over x, the reciprocal function, um, where you take an input x, take the reciprocal, that's the output y. And it produces this kind of function, and we have two asymptotes here, a horizontal one and a vertical one. The vertical one going directly down the y-axis there, so I've drawn it in a red dashed line there, you can faintly see, which occurs at x equals 0, because you imagine if you put x equals 0 into this, you get y equals 1 divided by 0, which is something we can't do. We can't divide by 0. This is what we call an undefined value. Um, well, the reason why that is simply is because you imagine what division is. You're basically asking how many times can you put one number into another. Like 10 divided by 2 is 5 because you can put 5 twos into 10. Well, if you do any number divided by 0, you're asking how many zeros go into that number. Well, it's essentially like infinite, isn't it? And that's what essentially produces this asymptote where you see it from the left it shoots down to negative infinity, or if you're coming from the right it shoots up to positive infinity. That's essentially the way to think of it. It's not equal to infinity, but it's tending to infinity as x goes to 0. So that's what a vertical asymptote is. It's essentially a completely undefined value. Like the function cannot cross that line. And then we have the horizontal asymptote here going along the x-axis, which is also at uh, 0, but y equals 0 this time. So that's basically, okay, what happens as x goes to positive infinity or negative infinity? Well, you can see y is basically going to go to 0, isn't it? So if x is just getting bigger and bigger and bigger, and we're doing 1 divided by that x, you can see y is going to end up becoming smaller and smaller. It will never quite equal 0, will it? Like even if x was equal to a billion, y will equal to 1 divided by a billion. That's a really small number, but it's still not quite 0, is it? So you see there, it keeps getting smaller, but it never quite reaches 0. So Um, how we would normally write that for the horizontal asymptote is something like this, and this is limits notation. So we would read this as the limit as x goes to infinity of 1 over x, which is our function, is equal to 0. That doesn't mean that 1 over x is equal to 0 at infinity, because you can't be at infinity. Infinity just goes on forever. But we're saying as x goes to infinity, as x is getting bigger and bigger and bigger, this 1 over x is converging to 0. That's what this notation essentially means. So it's a subtle distinction there. It's not equaling 0, it's approaching 0 as x goes towards infinity, as x gets bigger and bigger and bigger. So I'm hoping that concept is starting to make sense. So to summarize here, asymptote, we have vertical asymptote, which is basically happens when we are essentially dividing by 0. So whenever there's a division in your function, you should be thinking, what is happening with that denominator? When does that equal 0? Because that will produce vertical asymptotes. And then we also think of this idea of a limit, like what is going on as x goes to infinity, or as x goes to negative infinity. And that's what will produce a horizontal asymptote. And those are the two asymptotes that we have to be aware of. So let's take a more complicated example. That was a basic example of just y equals 1 over x. But say if we had a more complicated rational function, in general, we can find the vertical asymptotes by essentially finding the roots of the denominator. So when does that denominator equal to 0? Because we know that's when asymptotes occur. And we can use long division to find out where the horizontal asymptotes are going to occur. So the quotient of that long division will end up being what that horizontal asymptote is. So let me show you, with an example, and this should become clear. So say if we've got this rational function here. So rational function, so we had a little look at this before. Remember, it's just one polynomial divided by another polynomial. That's basically what a rational function is. And you can see here we've got one vertical asymptote going on here. So you see it's shooting up to infinity and then coming up from negative infinity as we read left to right. And where does that asymptote occur? At what x value does that occur? So you might want to pause here and take a think for yourself based on what you've just learned. So how we find that vertical asymptote? Remember, the vertical asymptotes are occurring when the denominator is equal to 0, because that just produces a completely undefined value because you're now divided by 0 and we can't have that. So, okay, when does the denominator of this function equal 0? Well, we can see it's when x is minus 2. If x plus 2 is the denominator, then when x is minus 2, that's what will produce a value of 0. So we can tell that's where that asymptote is going to be, at x equals minus 2. And we have a horizontal asymptote here. Where is that going to occur? So, okay, horizontal asymptotes can be a little bit trickier to find. That's where we then start using this limit notation. Okay, we want to find what is the limit of this as x goes to infinity, essentially. Well, what we can do is we can use long division here. So we saw this in our lesson on cubic polynomials. You might want to try using that now. Like again, if you want to pause here and try doing x plus 9 divided by x plus 2, it's going to be a very simple division. Only one step, really. And what you'll find is you'll get this. You'll divide by x plus 2. You'll get 1 with a remainder of 7. But that 7 still needs to be divided by x plus 2. That remainder still needs to be divided. It's just we can't divide it exactly. So it gets left like this. Now we can work out this limit. We find out, okay, what is this, the limit of this expression here going to be as x goes to infinity? Well, it's just going to be 1. Because you see that second term, the 7 over x plus 2, we've already seen if we've got 7, just a constant number, being divided by x plus 2, which is going to infinity. If x is going to infinity, then x plus 2 is going to infinity. Well, that second term is getting smaller and smaller and smaller. It's converging to 0. In which case, this overall expression is converging to 1, isn't it? It's essentially converging to 1 plus 0. So we get 1. And we can then put down our graph. That horizontal asymptote is going to be at 1. So I'm hoping that makes sense now, how that works. So we're basically looking for when does the denominator equal to 0? That will be your vertical asymptotes. And then we can use this long division technique, and you'll see that the remainder will basically go to 0 as x goes to infinity. And what's left over, what we call the quotient, which is 1 in this case, is what will be the horizontal asymptote. So let's take this up a notch again to uh, an even trickier one that we can get. But the key is that the same rules apply. Like, so whatever rational function you get, we're always going to work out horizontal and vertical asymptotes in the exact same way. Um, so, say if we have this one here, where there's quite a lot going on here. It's quite a complicated function. This time we've got a quadratic divided by another quadratic, and we get this graph going on here. But again, we work out in the exact same way. So if we want to find out where the vertical asymptote or asymptotes in this case, because you might be able to see there's going to be 2 here. And the reason why there's 2 is because, as usual, the vertical asymptotes occur when the denominator is 0. So it's basically when 2x squared minus 6x minus 8 is equal to 0. Well, that's a quadratic, isn't it? And we know in general a quadratic is going to have 2 solutions, hence why we see 2 asymptotes here. So this is something that you should have no problem solving yourself. Quadratic, we can simplify this first of all by dividing by 2, and then we can factorize, and you should get these 2 values for x. And so there you go. You see, we're going to get 2 vertical asymptotes. One at x equals minus 4 and one at x equals 1, because those are the 2 values where that denominator is going to equal to 0, and therefore y is going to equal to something divided by 0, which we know is something we can't do. That's an undefined value, so it produces these asymptotes. Now the horizontal asymptote is going to be a little bit trickier. We need to find the limit of this expression here as x goes to infinity. Now we can do this the same way as before, where we'll do a long division, but we haven't really seen long division with like when we're divided by something more than a linear expression. Like here we've got a quadratic. You can work out in very much the same way, and I would encourage you to give it a go. But in a case like this, where the degree of the 2 polynomials on the numerator and the denominator are the same, like in this case, they're both quadratics, we can simplify this a lot by using, again, remember back to when we was looking at cubic polynomials and how we determined whether it goes like from like negative infinity to positive infinity or the other way around. We looked at the leading terms, because as x goes to infinity, the leading terms, that is the terms with the highest power of x, they're going to dominate as x goes to infinity, because they're just going to grow so much faster than the other terms. So when we're just trying to find a limit like this, we can actually ignore all the other terms and just look at the highest order term on the numerator, and then the highest like power of x on the denominator as well. So we just take the x squared terms. And this division is very simple to do, isn't it? You see, it's just going to come out to 2. And so we find that horizontal asymptote is going to just be at y equals 2. So that's a way we can work this out a lot easier. Like when we're looking at limits as x goes to infinity or negative infinity, we only really need to look at the leading terms. If the numerator, if the highest powers of the numerator and denominator are the same, or if perhaps the denominator's power is higher, if the numerator's power is higher, it doesn't work quite the same, but that goes a bit beyond the scope of GCSE math, so we don't really have to worry about that. So there you go. So you see, we're essentially, it's the same concept. So we look at when the denominator is equal to zero, we'll produce the vertical asymptotes, horizontal asymptote. We need to essentially do this long division, or we can do something like this where we just look at the leading terms and we can quite quickly work out what that horizontal asymptote is going to be. So what I'll do now is quickly skim through some um, more peculiar cases you could come across, but most of them are going to be similar to what we've just seen. Like there's not really much that you can be asked about rational expressions. Um, so um, one thing to remember is that the number of roots of a polynomial can vary depending on the coefficient. So you should already be familiar with this, certainly with quadratics, that in general, yes, we get two solutions. Sometimes we only get one. Sometimes we don't get any. So this will affect the number of vertical asymptotes. So say if we take an example like this. So you see here, we've got 5 divided by this quadratic. You would expect there to be two vertical asymptotes because that denominator in general would have two roots. It will have two values where it equals 0. But in this case, you see there's only one um, vertical asymptote. So I'd encourage you to find the roots of that quadratic to determine where these two asymptotes are going to be, or supposed two asymptotes will be, and you'll see why in this case actually there's only one. So yeah, pause here and try that yourself if you want. Otherwise, let's look at the next one, which would be one like this, where you see we've got a linear expression divided by a quadratic. Again, that denominator is a quadratic, so you'd expect there to be two values where it's going to equal to 0. In which case you would expect there to be two vertical asymptotes. But in this case, we actually have no vertical asymptotes. And again, I would encourage you, to take a look at this using what we've just seen, how the roots of the denominator correspond to vertical asymptotes, and prove to yourself, why this has no vertical asymptotes. And finally, we've got one like this, which is what we're going to look at in more detail now in the next section of this lesson. Because here you'll see that again there is a quadratic on the denominator, so you'd expect there to be two vertical asymptotes, but there isn't. There's only one. But there's only one, not for the same reason as before, not because that denominator only has one root. It still has two distinct roots, but it has what's known as a removable discontinuity, which is what we're going to look at now. So the second section, we're now going to look a lot more into these limits of rational expressions and how we would calculate them just mathematically, not necessarily graphically. So a rational expression is an algebraic fraction, essentially, where both numerator and denominator of the fraction are polynomials. So we've already seen that. We've seen how this can often result in a discontinuity if or when the denominator of this algebraic fraction is equal to 0. So a discontinuity, what does that mean? So a continuous line is one, you imagine if you could draw it on a piece of paper without taking the pen off the paper. So you imagine you could just draw the line continuously like that. But you see here, it's with these rational expressions that we've been looking at, it's not continuous because you see we've got these asymptotes and it results in essentially like a gap. Like you see we're going down and then we'd have to bring our pen up here to then come back down from the top. You see how it shoots down to negative infinity and then essentially comes back down from positive infinity at these asymptotes. That's a discontinuity. And at that value of the asymptote is essentially a gap in the graph because the function cannot equal that value. So that's what we refer to as a discontinuity. It's like gap in the graph because of that undefined value. But sometimes we have algebraic fractions or rational expressions more specifically, where it appears like there's a discontinuity, but there actually isn't. And by finding the limit of the value of the function as it approaches that discontinuity, we can kind of do some algebraic techniques to show that it's not a discontinuity and actually remove that discontinuity. Hence why we call it a removable discontinuity. Um, so um, what we've looked at so far are discontinuities that cannot be removed. So it'd be something like this. We see when we substitute x equals -3, we get -3 over 0 in this case, which is an undefined value because we can't divide by 0. And so therefore the limit as x goes to -3 is basically plus or minus infinity. So this is what we've seen so far. A discontinuity goes to positive or negative infinity, can't be removed. We're going to look at ones where they can be removed. So how do we identify when there's a discontinuity that can be removed? Well, we're always going to get that whenever we have a rational expression that evaluates to 0 over 0 for a particular input value, which is obviously an undefined value, um, but it can be removed due to the factor theorem. So if you remember back to what we was doing on cubic polynomials with the factor theorem, so say if we had a solution, basically a root of a polynomial, basically when that polynomial is going to equal to 0, say if that occurs at a value of x equals 2. The factor theorem tells us that then x minus 2 is going to be a factor of that polynomial. Well, if we have a situation here where we have a polynomial divided by another polynomial and they both have a root, they both equal to 0 at a particular value, like say x equals 2, that means they're both going to have a factor of x equals -2, and therefore we can cancel out that factor because we're doing one divided by the other. So this is the idea behind removing that discontinuity, is we find that common factor, we can cancel it out. Um, so yeah, so that's the key. Now, that may or may not make sense. Let me show you with an example, and I think it'll become a lot clearer. So say if we've got this function here, this algebraic expression, sorry, this rational expression where we've got a polynomial divided by another polynomial. We're dividing by this little linear polynomial here, x minus 1. And so one would expect there is going to be a discontinuity at x equals 1 because you're going to get 0 on the denominator there. So what we're doing is we're going to try and find the limit as x goes to 1 and see, does that go to positive or negative infinity? Well, is there any kind of algebraic expression manipulation we can do with this here to um, essentially remove this discontinuity, or is it just not possible to be removed? So, like I alluded to a moment ago, we need to factorize. So the denominator, there's nothing to factorize there, but on the numerator, there's a cubic polynomial there, and we can factorize out an x straight away. So this is quite a nice one to factorize. We can factorize out a common factor of x there straight away, and you see what's left in the bracket is a quadratic. And in further maths, you should already be very, very familiar with factorizing quadratics. You see we can factorize that into x minus 1 and x minus 2. And notice what's happened here. We've got that common factor of x minus 1 that's appeared. And so we can cancel that out because we're doing x minus 1 divided by x minus 1. We're essentially just going to be left over with x and x minus 2 as factors. And notice now, we can substitute in x equals 1. That's not a problem anymore because we're just going to get 1 times -1, which is -1. So therefore, we've shown here that at that value of x equals 1, where first of all it appeared like there's going to be a discontinuity, there actually isn't. It's actually going to equal to it's going to actually equal to -1. Y equals -1 when x equals 1. So that's an example of a removable discontinuity there. Let's look at another example here, a bit more of a complicated one where we've got a quadratic over a quadratic. Again, we haven't got a graph here. We're trying to determine how many discontinuities does this actually have. At first glance, it would appear like there's going to be 2 because we're dividing by a quadratic there, but there might not be. So let's see. Say if we're trying to find when x is going to equal to 2. Because if you substitute in 2 into the numerator and the denominator there, you'll find they'll both come out to 0. And, okay, so at x equals 2, this essentially equals to 0 over 0. Like we've just seen, um, that indicates that there's a removable discontinuity here. So that's normally a good first step, is just substitute in that value and see, does it evaluate 0 over 0? If it does, that indicates that there is a removable discontinuity. So, okay, we've already seen what we need to do is we need to find a common factor that we can cancel out. So if we factorize the top and the bottom, two quadratics should be very straightforward to factorize these. And you see we end up getting this. And notice again, we get a common factor of x minus 2. And we can cancel that out and we get x over x plus 3. Now notice this expression still has a discontinuity at x equals minus 3. But we're not looking at that one. We're looking at when x equals 2. And notice here, we can substitute in x equals 2 now and not have any problems. We get y equals 2 fifths. So we find that x equals 2, y equals 2 fifths. It's not actually a discontinuity. It doesn't go to positive or negative infinity. It's just 2 fifths. So again, so this is an example of one that looked like it potentially had 2, but actually only had 1. This was the one that I referred to earlier, where, yeah, you would expect it to have a singularity at 2 and minus 3, like vertical discontinuities. Sometimes I refer to them as singularities. It's kind of the same thing. Yeah, but we see actually there's only a discontinuity at x equals minus 3 because the one at x equals 2 can be removed in this way. So this here is really important because we're going to be using this a lot when we're trying to do a technique what we call differentiation, which is what we're going to be looking at next time. One of the main pillars of calculus that you'll be learning about as part of your further maths. So I hope now you've got a good understanding of what limits are, because we're going to definitely need them in the next lesson. Here's your challenge question for today. So, say if I draw some axes here, and I'm going to draw this graph here, quite a complicated graph going on here, with this rational expression. And what I essentially want you to do is try and find what are all the asymptotes of this graph. So this is one that everyone should be able to at least do the first step of, which is to find the vertical asymptotes. And you can see here that there's 2 vertical asymptotes here, which we've seen is basically whenever the denominator is going to be equal to 0. That should be something everyone has no problem with now, and you should be able to find where these 2 vertical asymptotes are going to be. But what you might also notice, this one here doesn't have a horizontal asymptote. It actually has a slanted one like this. And you can work this one out using the same techniques that we've done today, where we have to do a long division. So we've seen the roots of the denominator tell us the vertical asymptotes. But if we do this long division, it will tell us what this the equation of this slanted asymptote is going to be. It's basically going to be an equation of a straight line. The reason why we get a slanted one here is because the degree of the polynomial on the numerator is higher than the one on the denominator. So we've got a cubic over a quadratic, and that's why we get a slanted asymptote like that. This is a bit beyond the scope of further maths. I'm just setting this as a challenge question for anyone who just wants that additional challenge. Like I said, with the techniques we've learned today, you can work this out. You need to be able to do that long division with a quadratic in this case. So you might need to look up how to do that, or perhaps your intuition can guide you. But yeah, feel free to have a go at that and see if you can work that out. If you can, yeah, very well done, because that is quite tricky. But yeah, let's leave it there. So that's our takeaways for today's lesson. Make sure you understand all those items on the checklist. Make sure you're comfortable with this idea of limits at the very least, because we're going to need to use that in the next lesson, where we look at differentiation, which is all about the study of gradients and rates of change, and how do we find these in the general case, not just for a linear case, which you perhaps, well, not perhaps, you've certainly already seen. we're going to see how do we do this for the general case. So I will see you in the next lesson for that.